So this video is about learning math using contemporary methods, using coding, using computers, using various new technologies that we have today with us. So this first slide is all about learning calculus, and for the purpose of demonstration, I have picked up this text from NCRT Class 12 Math book. Uh, the way differentiation is being taught in that chapter is still very old-fashioned and quite intimidating. Uh, is there a better way in which this can be learned? That's what this presentation is all about. So let's try to dissect what this complicated looking formula is doing here. So this is what differentiation is all about. Ironically, it's the most simplest mathematical operation. As you can see that it just takes only one subtraction and one division operation. But the way it's taught it looks very confusing and complicated. So let's try to understand what this formula is all about. So, so firstly, we have to understand what this f is all about, which is in mathematics it's called a function. F is nothing but it's just a rule which maps numbers on the x-axis to the numbers on y-axis. It's as simple as that. For example, f can be a sine function, cosine function, log, exponential. It can be anything. So for this particular example, I have taken sine as a function, and what I'm trying to show here is that there are numbers on the x-axis which are shown in this column, which are the input to the sine function. And once this input goes into this function, this law, this rule, it spits out a different set of numbers. So function is nothing. It takes one set of numbers, generally from the x-axis, and it spits different kind of number, which basically forms the y-axis. So in case of sine function, this is how it looks. We have x-axis here, which is starting from 0 and going up to almost 2 pi. And then using this law of sine, it is generating some y values. So let's take some examples here. When x is 0, as per sine law, y also is 0, which is what this table is also showing, this entry here. When x is 3.14, which is this point, which is nothing but pi, the output of y, the output of sine function goes to 0, which is what this third entry is doing. And lastly, if you see this x number, which is 6.28, which is nothing but 2 pi, when it is fed in the sine function, the output of sine function is 0. So with these three numbers, 0, 3.14, and 6.28, when we feed these numbers in a function called sine, it generates nil output. Let's talk about this number here. This is x value of 1.57. When this number is inputted in sine function, it generates 1, which is what this entry is all about. And 1.57 is nothing but pi by 2. And when we come to this particular number, which is 4.71 on x-axis, when this number is given as input to sine, it generates -1, which is what this entry is all about. So essentially speaking, this is what is the definition of function. In the most simplest manner, it is a law which takes x-axis as numbers and outputs y-axis, and there's nothing more to it. And this numerator part in this whole formula is all about this. So let's go further and dissect what this denominator is all about. This denominator is nothing. All it is conveying is that the increment in your x-axis have to be a small step. Like in this case, we are starting from 0 and then we are jumping to 1.57. So this h is nothing but 1.57. And the next step is also like this. When we subtract 3.14 from 1.57, we again will get 1.57. So h is nothing. It is just a small increment in the x-axis. And we have to keep on incrementing x-axis like this and form the denominator part of this equation. Moving further, this complicated looking part, it just conveys only one thing. It says that don't increment your axis the way it is shown here in very large steps. It should be as small as possible, very close to 0. For example, 0.1, 0.01, something like that, but not in the manner that has been shown here. So this complicated looking thing, limit h tending to 0, is just a representation of the fact that do not increment your x-axis in large steps. Moving further. Now this numerator is nothing but change in y-axis in correspondence with the changes in the x-axis. So we are incrementing x-axis by a small step, and we are trying to see its effect on the y-axis. For example, here we incremented the x-axis by 1.57, and y-axis has changed from 0 to 1. So there's a delta change in y-axis of 1. And this complicated looking formula is what it's saying is that take your current sample of y-axis and subtract it from the past sample, essentially to measure the change in y-axis which has happened because you have incremented your x-axis by h. That's all there is to differentiation. It looks complicated when it is solved analytically, but let's see if we can do some justice to it by implementing it in code. So here we are in the environment called Jupyter Lab. This is a Python environment, absolutely free of cost, nothing to be paid. I assume that the viewers don't have any knowledge about Python. So I'll keep it simple. The core idea here is to demonstrate that math can be easily learned using coding. This lecture is not about teaching the syntax of Python. So in the first cell, I'm importing some libraries from Python. NumPy stands for numerical Python. It is imported in this environment and given a nickname or an alias for NP, and then some plotting libraries, etc., to set up the environment. Coming to the differentiation, how this can be implemented in code. So if you remember, we had said that firstly we have to decide a small increment in x-axis or dx, which is also the denominator of the differentiation formula. So let's start with that. Let's declare a variable h, and as the differentiation formula has taught us that it has to be kept as small as possible. So let's choose a very small number. Let's say it's 0.01. So now this is the incremental step in which the x-axis will be incremented. The next step now is to generate the x-axis itself. Now for that to happen, we must decide what is the start point of the x-axis and what is the end point of the x-axis. So let's define a variable x start and let it start from minus 2 pi and let it end at 2 pi. All right. So now we need to generate the complete x-axis. So for that, I declare a variable x and I use a function from NumPy library. It's called arrange. I will not go into specific of what it does, but I'll show you what is the output of this function. So it takes a number which is the start point of an array, and you have to specify a stop for it and in what increments you want these numbers to get generated. So let's see what this function has done. Let's print out these numbers. So there you are. We wanted our x numbers to start from minus 2 pi. So array has been initiated, which is starting from minus 6.28, which is nothing but minus 2 pi. And it is going up to plus 6.28. This dot 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 shows here that it has skipped certain numbers for the ease of printing on screen. So the next step is to figure out how many such numbers were created. So for this we just use a variable. We'll just declare a variable numx, and we basically want to check the length of x-axis. How many numbers are there in x-axis? And let's just print it out. So it says 1,257 numbers have been printed. Now this shows that the x-axis is being incremented in a very, very small manner, which is each increment is just about 0.01, which is also a dx part of the equation or the denominator part of the equation. And our axis is varying from minus 2 pi to plus 2 pi, and it comprises of 1,257 numbers. That's all that it is conveying. So here we have successfully generated the x-axis or the denominator part of the differentiation. Now let's start building the y-axis. For that, we have to first define the function itself. So let's say my function y is sine function, and in this sine function, I'm going to input all the numbers of my x-axis. This is how it's done, and let's see what it generates. So you can see here that it starts off with a very small number, and it ends also on a very small number, which goes on to show because sine of 2 pi minus 2 pi is 0, and this is exactly what this array is doing. But it's not very clear from this whether actually it is a sine function or not. So we'll do one thing. We are going to have a visual appreciation of what's going on. So for that, let's quickly plot our function. So we will generate an x-axis, we will generate a y-axis, and we quickly want to see and verify whether we are indeed dealing with sine function or not. So there you are. We can very quickly see that our function is a sine function, which is starting from minus 2 pi going up to 2 pi. So far so good. We can actually see things happening now instead of solving it by hand or analytically. Moving on. Now we have to calculate the numerator part of differentiation. Numerator part is nothing but changes in the y-axis. And as the formula goes, we have to find the dy, and dy is nothing. It is the current sample of y-axis minus the previous sample. Now, how do we retrieve these numbers from the y-axis? I will just quickly show you that. For that, Python uses a little trick. So I'll just show you that trick. So firstly, let's just print out the y-axis, and here is the y-axis. So let's say if I have to pull out the very first number from this array, so the syntax for that is simple. All I have to do is just specify the index, and in Python, index starts from 0. What this is saying is give me the first number of the array, of the y array. There it is. So if I want to have the second number, I'll just have to increment it by 1, and I'll get the second number from the array. Right. So we have figured out a way to retrieve numbers from an array by using this simple syntax. And why is it required? Because we have to retrieve the current sample from the array, and we also have to retrieve the previous sample from the array and subtract it. So how do we go about doing it? So even before we go there, I would like to initialize the array where I'm going to store all my results, all my increments and y-axis. So let me just initialize an array of length x where I'm going to save all my dy results. Let's see what this array looks like. As you can see, this is all zeros, and this dy array is containing all zeros, and these zeros will be soon replaced with the actual calculated values of dy. So now moving on to how to go about calculating the numerator of the differentiation formula. So I'll do one thing. I'll just make use of a simple for loop, which is what this little line of code is saying is that go through all the indexes in the y, which is starting from 0 and going up to 1257. And for some reason, which I'll explain later, it has to be minus 1. And build your array, build your dy array, start populating it. And the first element, the ith element of the array will be equal to, so we have to retrieve the first sample or the current sample minus the previous sample from the y array. This is what is the formula of differentiation. And this is how it's going to get implemented in the code, just one line of code. And let's see what this dy array is all about. We print it, and we see that it has given some numbers. Whether they are making sense or not, we'll just see it. So a lot of numbers have been given, generated, and let's see what is the length of this array. It has given exactly the same numbers that we started off with. If you remember, we generated x-axis, which were 1257 numbers. Then we generated y-axis, which were again 1257 numbers, making the sine wave. And now we have generated the change in y-axis, which is again 1257 numbers. So let's start analyzing these things visually. Firstly, I have to calculate the derivative, which was nothing but numerator by denominator. So I'll call this as dy dx. And all I'm going to do is my dy array divided by my dx, which was nothing but h. So that's all there is to differentiation when implemented on computers. As I told you earlier also that differentiation when implemented in computers is nothing but one subtraction operation and one division operation. That's all. There's nothing much to it. Let's see what this dy dx array is all about. So again, it's an array of numbers, and we'll try to make sense of this particular array. So let's start plotting everything so that we have visual appreciation. Let's start with the function itself, which is the sine function. So the syntax for that is I have to first give input my x-axis, then I have to input my y-axis, and then I can see what's happening here. Just let's keep it simple. There you are. This we have done earlier also, and we know that we are generating the sine wave correctly, which means our function is correct. Now we have to see the derivative of that function, whether that has been computed correctly or not. Theory says that if you differentiate a sine function, what you get is a cos function. Have we been able to get it? Let's just check. So we are just going to generate one more plot, and instead of generating the function this time, we are going to generate the derivative of it. There we are. Well, this matches with the theory. We took a sine function and we differentiated it using first principles, and this orange line that you're seeing is nothing but cos wave, and which is matching with the theory. The differentiation of the derivative of sine is cos. Let's just make this plot slightly more beautiful by giving it some labels. So this is, I'll call it sine function, sine of x, and I will call this as differentiation of sine of x, and I will do some modification here. We show these legends. So right now there's no legend here. You'll see once I execute this code, the legends will appear. There they are. So now the blue line is the sine line, and the differentiation of sine x, which is cos x, is the orange line. Let's take it further. Now in the end, if you're seeing this derivative is falling to 0, we can correct this by ignoring the last sample of this array. And how we can do it is using a very simple line of code. We are ignoring the last sample so that we get a better plot. There we are. So this drop into 0 has gone. It would be so much better if you could see the grid uh, behind these curves. So I'll activate that. And there we are. Now we can very clearly see the graph. At 0, our sine wave is 0, and at x is equal to 0, our cos wave is at 1, which is exactly what the theory says. Now we can further improve this plot. I would like to have names of these axes here, so I can use that. I will say I will name my x-axis. There I am, so I can see x-axis here, and then I can also label my y-axis. And there I am. This y-axis is now appearing here. I would also like a title to this plot. I will call it function and its derivative, and the title of the plot appears. I also want these 0 lines to be highlighted. 0 here, the vertical direction, and 0 in the horizontal direction. So let me do that. So I have to specify the color, and I'm going to use K is the code for black color, and I want to use the dashed lines. So line style, I will specify as dash dash. When I execute this code, you see this dash line appears here, and now I can also generate the y line or the vertical line. There we go. So now this looks much better. Clearly, by understanding the formula and then implementing it in code, we have been able to verify that differentiation really works. Let's put it to test. Now we know that our code is functioning fine. Let's start experimenting with some other functions. For example, now we can change this sign to cosine function. And what the theory says is that if you differentiate a cos function, your result is minus sine. That is the inverted version of sine should appear. Let's see if that happens. There we are. So the blue is our original function, the cos function, and the differentiation of it is inverted sine wave, which is minus sine. And this visual appreciation is matching with what the theory says. Let's experiment further. That's the beauty of learning maths in code, because once your code starts functioning, once your basic building blocks are in place, then you can do a whole lot of experimentation. Let's change this exponential cos function to exponential function. What theory says is that if you differentiate an exponential, you will get the exponential function back. Let's see if it happens. And there we are. So we have, you can't see the blue line here, so we can do some corrections to see it. I will, I will change the line style and color. So you can see now that between these black and blue lines, in fact, black is not very visible here, so let me just change it to some other color. Let's red. So exponential and it's differential are overlapping. So both these lines are overlapping, and that's the reason why they are you're not able to see very clearly what's happening behind the scenes. I can increase actually the thickness of one of them, but you get the idea. So this is how maths can be taught. A very simple thing which looks very complicated when solving analytically, namely differential calculus. Just by writing few lines of code on an absolutely free software, you can start learning it pretty quickly. More importantly, you can start appreciating it visually. What's going on here? For example, let's say we have to plot a logarithmic function here, and we know that log of negative doesn't exist. So immediately this should throw some errors. There we are. Uh, it says that there are invalid values because what has happened here is, if you see clearly, if you see closely, our x-axis is starting from a negative number, and that's the reason since the log of negative does not exist, it is throwing errors. Also, log of 0 is negative infinity, which is again a problem. So let's define a very small positive number from where our x-axis is going to start, and let's keep it in positive direction only. So now we should be able to plot it. So as you can see, this dotted line is the log function, and the derivative of it is like this, which is nothing but 1 by x. And in fact, we can prove that we can actually plot a 1 by x function here and prove that derivative of log is is nothing but 1 by x. There we are. I have taken 1 by x and plotted it in magenta color, and you can see that magenta and blue lines are overlapping, which means what we have obtained as a derivative of log is matching with the theory part. The derivative of log is 1 by x, and which is what we can clearly see in the visual representation also. So that's all. For the point that I wanted to convey was that it's so much easier to learn maths, so much fun to learn maths if we do it the right way. If we use the tools, if we use the contemporary technologies which are available to the students now, rather than just doing it by hand and doing it analytically. Thank you.